All right, so you should see my screen right now. So in this talk, I want to try to give you an overview of what it means to work with computer vision models hosted on the Hugging Face Hub. So it's it's a bit of a whirlwind tour of the different features that we have in there. From how do I find a model to how do I train one? What are the options for deployment, etc., etc. So the first thing, and I guess it should be obvious to everyone here, is that computer vision is really, really important. I remember when I first got involved with deep learning around, I would say 2015. I guess what got me into it was computer vision, and of course the ImageNet data set and the ImageNet related competitions, etc., etc. And in everybody's opinion, when you say deep learning, especially when you're talking to developers and people who are less familiar with the science part of deep learning, immediately they'll talk about computer vision. It's very striking. Anyone can understand it. You can do demos to business users and stakeholders with images and videos, indeed. And they'll immediately understand what you're showing them. Sometimes, with NLP or other types of data, other modalities, it's not so obvious. So obviously, computer vision is critical, and a lot of enterprise customers and startup customers are really keen to build computer vision use cases. And for a lot of time, that really meant working with convolutional neural networks. So I'm guessing everybody here is familiar with CNNs, so I won't go into all the details. But I think the key thing I want to mention here is we train CNNs on image data sets, and the purpose of that is to learn the convolution filters that will extract the right features, right, whatever that means, and then classify or detect images accordingly. And as we do this, we throw, or I should say, the model throws a lot of pixels away. We focus on edges and geometric features, etc., etc., and we apply pooling, and along the way, we end up throwing a lot of pixels, and hopefully we keep the important ones. And obviously, CNNs are great. That 2021 date is definitely not a death certificate for CNNs. Far from that. They're still heavily used, and they're still evolving, and they're still being mixed with transformer models. But I think the golden age of CNNs is probably behind us. And the guilty party here, as we all know, is the vision transformer that Google released and published almost 2 years ago now. And as the name implies, it uses a transformer architecture. So that gray box on the slide is I would say the vanilla transformer architecture with the attention mechanism and so on. And the clever bit, I think, in the vision transformer is, well, how do you treat an image as a sequence of tokens? Because that's what transformers are, really. They take a sequence of tokens, originally, obviously, NLP tokens, and then they learn the dependencies between those tokens, and they build all kind of interesting things with that. And the way they've done it is, first they split the image in patches, okay, and then they flatten those patches, and they treat those patches as a sequence of tokens, and they use a position marker as well to give that information to the model of what's the relative position of those different patches. And amazingly, applying this NLP-ish technique to images has proven to be extremely efficient. And you can see some benchmarks from the research paper on the slide. And this one compares the Vision Transformer to ResNet 152, which is kind of state of the art at the time. And it's generally, doing quite a bit better. So that's really interesting. I think the key difference here is that we are not throwing any pixel away. We're considering every single pixel in the image, and we're just applying that sequence magic to images, which generally did not work at all with fully connected networks, etc. So I guess the attention mechanism here works magically again. So this was the first step, and obviously a lot of models followed, but generally what you can say about vision transformers is they do deliver state-of-the-art accuracy, and state-of-the-art is a very fleeting concept, I know, but generally, even if the vision transformer today isn't the best, other more recent transformers still keep improving on the metrics, whether they're accuracy or something else. Interestingly, in that paper, we also learned that training this model, and of course, Google being Google, they use TPUs, was in fact 4 times less compute intensive than training ResNet 152. So that might not hold for all models, but generally, I think this is an interesting thing to keep in mind. And of course, transfer learning is is kind of built in. Transfer learning is one of the, I guess, to me, the most interesting property of transformers, whether they're NLP or computer vision or something else, is that you can go and you can build your pile of data, your millions and tens of millions of data instances, and train your model initially on that, learn the embeddings, and then specialize that model for downstream tasks, potentially throwing some of your own data into the mix, but I guess just a little bit. So transfer learning is key to the success of transformers, and that's also true for images. And as of 2 years ago, almost 3 years ago, when you talked about transformers, obviously you really meant NLP, right? I mean, Google BERT was released in 2018. And NLP was the number one use case for that. So, a couple of years after that, people were still focusing on NLP, right? And you can see in around 2020, only 2% of research papers using transformers were computer vision related. Now, if you fast forward 2 years, NLP is still the biggest chunk, but it's less than 50%. And we can see this 11x increase in computer vision transformer research, and video goes from literally 0 to 5% as well. So no surprise, because like I said, computer vision put deep learning on the IT radar for enterprise, and it makes a lot of sense to me that people would try to go and capture that market, so to speak, with transformer models as well. So I expect to see this 22% number to increase very, very significantly, because there are so many computer vision use cases out there. So that brings me to Hugging Face, which I guess answers the question of okay, transformers, nice, but where do I find them? How do I use them? Is it complicated to use them? And anyone who tried to actually use BERT out of the box in 2018, going to the GitHub repo, would say, yeah, that was difficult. It was hard for me to even understand what to do with the weights and the fine-tuning scripts, and it was painful. So that's really the problem we're trying to solve at Hugging Face. We're trying to build open source libraries and a website and commercial tools that make it very easy to work with those state-of-the-art models, even if you're not an expert. And in that respect, a lot of people call us the GitHub of machine learning, which I think is a decent analogy. We all go to GitHub to share code and find code for our projects. And I guess, a lot of people go to the Hugging Face Hub to find models and share models. And so when I updated this slide a few days ago, we had 110K models, and I just checked before the session, and I think we're at 120K plus. So it's an insane number of models being added every day. Probably, more than 1,000 models every day. So yeah, 100K plus models, about 18K data sets. And of course, a lot of that stuff is transformer related, but we also support 25 plus all machine learning libraries. So what that means is you can actually find Keras models or scikit-learn models or FastAI models on the hub, and use them and enjoy the user interface and all the bells and whistles that are built into the hub, just like you would with transformer models. We have about 10,000 organizations contributing models, from, of course, Google to Meta to Microsoft to research labs, universities, and of course, individual developers, right? Training cool models and sharing them. And day in, day out, we have about 100,000 active users and about 1 million model downloads every day, sometimes much more when something big and popular is released. So zooming in on computer vision, we have about 4,000 models for a variety of tasks, from I guess the usual stuff, image classification, object detection, all the way to the crazy generative models, which we'll take a look at. And I've broken down those models into 4 categories. So we've integrated the PyTorch Image Models. I'm sure a lot of you are using that really cool library called timm from Ross Whiteman, and Ross is actually working for Hugging Face and integrating the models there. Of course, the bulk of those models are computer vision transformers, and we'll look at those. And we'll also take a look at some of the multimodal transformers that we have. Those are really, really interesting, mixing NLP and images, or speech and images. Really, really interesting. And we can see the synergy between the different modalities there. And of course, everybody's favorite models these days, the generative models, stable diffusions, etc., and the diffusers library that we built. So first of all, we have, like I said, the models from the timm library. We have about 300 models. And in a nutshell, timm is just a super cool collection of computer vision models. A lot of them are actually not transformer related. That library has been going on for years. So you'll find the more traditional architectures, ResNet, ResNext, MobileNet, etc., etc. And also of course, some transformer models that Ross is building and fine-tuning on different data sets. And there's a huge variety for the same model. You'll find lots of different versions, and I think that's why people love timm. And those models are now available on the Hugging Face Hub, so you can just basically pull them from there. You can see that code snippet here. It's very simple. Just grab in this case a convnext model from the hub. And create a configuration, create a transform, load an image, transform it, and then predict it with the model. So super simple, and just at the one line just pulls the model from the hub, and you don't have to worry about loading it from anywhere else. So if you've been using timm so far, well, now you can just pull the models from the hub, find them on the hub, engage on discussions. On the hub, we have this community tab on the model pages where you can ask questions, maybe send pull requests, etc., etc. So you can go into that. Super cool to have those this extended collection of models available there. Well, the next category is, of course, I would say the the bulk of those CV models. And there are, of course, the transformer models. And so let's just take a look at the hub for a second. Let me zoom in. Oops, not too much. So, if we go to models and to the task types here, we'll find our task types, and we can just go and grab, we can see we have 1,700 plus models for classification. They're sorted by downloads, which I guess is a good popularity metric. And you can just go and grab any of those, okay, and learn what that model is all about and what it's been trained on, code snippets, etc., etc. If you use Hugging Face already, you already know this stuff. But hey, I'm thinking, maybe someone here has never used Hugging Face, so that's why I'm showing this. Code snippets to download the models, code snippets to train and deploy models. I'll mention some of those things later on. And of course, the inference widget, where you can just go and predict images right there, right? Links to data sets that the model has been trained on, ImageNet 1K, right? And of course, links to spaces, right? And we'll look at spaces in a few minutes. So there you go. So you can just go and do do all of this for any of the models. So models for image classification, models for zero-shot image classification, go and test them, etc., etc. And I've actually built. Where's that space? Nope. All right, give me a second. Too many browsers in here. So here's a space, and spaces are potentially one of the coolest. Well, I'm going to call it the coolest Hugging Face feature right now. So space is basically a small application, right, that you can write, and I'll show you this one. So write this using Streamlit or Gradio, and create a repository on the Hugging Face hub, push the code there, and automatically this fires up a container running your app, and so it's all managed on our infrastructure. So here, I'm just starting from a bunch of classification models, and I'm building a simple UI, which we'll look at in a second, and I'm writing a simple process function that gets invoked when I click on the button, and of course that process function, as you can see, is going to predict an image with all of those models and display the results. Okay, and I'm using the super simple pipeline API from the Transformers library, so that's all it takes to load a model and predict it, right? So 52 lines of very simple code. And obviously now I've got this app running, so let's go and grab a sample image here, okay, and predict it. So now I'm predicting it with those, 10 or 12 different models, and I'm going to display the top 5 labels. Okay. So you can see how simple it is to go and experiment with the models. Unfortunately, sometimes it takes too much time to even figure out what a model does and how to use it, and how to test it on your own data, etc., etc. And here, it's super simple. It's literally 2 lines with a pipeline and just a few lines of Gradio code to build this simple app. And we can see the different predictions, right? Just like that. Okay, so that's all it took. 52 lines of code, and again, very, very simple code. And create a repo on the hub and push it there, right? And it's 52 lines because because my formatting makes it 52 lines, but it's really, it's much simpler than that. So that's really the kind of stuff you can build with Hugging Face these days. So if you've never looked at spaces in particular, I really, really encourage you to do that. Maybe you've been playing with existing spaces, but building your own is simple as well. And we always need more. So obviously, detection, segmentation. We have all those models. We have all the the top ones, and actually a lot of those teams, publish. They push the paper to archive, and then within a couple of hours, they push the model to Hugging Face. So by the time you read the paper, it's very likely you can go to Hugging Face and find the model there. And again, looking at the code, that's all it takes, right? Here I'm just running a simple prediction on simple object detection, and all the models on the hub can work that way, right? Just create a pipeline with a task type, point at the model you want to predict with, and then just go and run your pipeline just like that. So when you're experimenting, and I mean even for production, and if you don't need any particular pre-processing on the data, if you're not doing anything super fancy, you can run the pipeline for production just like that. Couldn't be simpler. So now, what about the more advanced models? I could pick a lot of those, but I picked 3. So image captioning and zero-shot segmentation using a text prompt, and audio classification using spectrogram. So these are more recent models. So we can go again and look at them with a space. So let's take a look at the code too. I'm curious how much code this is. All right, well, so downloading some models and generating captions and building the interface. So you can see, this isn't complicated. You can write this thing in an hour or 2. It's very generic code. You can steal the code and customize it. So let's go. Why don't we try this? Okay. Right. So here, we use those image captioning models. So you could call them, I guess, image to text, right? And again, it's interesting to see the different results from those different models. We can see the models here. So you can see a couple come from Microsoft, a couple come from Salesforce, and this one is from NLP Connect. And we can see the data sets here, right? So just like that, you can build some interesting applications. And I think that's where the transformer architecture is really cool, because in a way, we use the same building block, which is again the transformer building block and the attention layers, and so we can combine. We can apply that stuff to images and to NLP, and so those models building blocks tend to work very well together. And there's a lot of interesting work happening on multimodal, because again, an NLP transformer and an NLP computer vision model will, I would say, naturally integrate into something pretty cool. So this one is this one is ClipSeg. So this one is image segmentation. So let's grab an image. I'm gonna grab my image here. And this is zero shot, right? So I don't need to train it, and I just want to say find maybe the helmet. Okay, and I'm going to get a heat map here, pointing at the object in this case, and its location in the image, right? So that's a very interesting application. This used to be very, very difficult to build with, I would say, traditional CNNs. And here the code is just, as simple as it is, right? You just load the model, predict the image, and that's it. So again, you don't need to be a machine learning expert to do that, right? If you're, just a developer, a normal developer, and I mean that in a very positive way, you can do this thing. And here's one I really like. So this is actually this is an older space that I built using initially a model called Wave2Vec2 Conformer, which is a mix of convolution and transformer. And this is a Facebook model for audio classification. And just a I guess a few weeks ago, a new model came out, or it became available in Transformer library. It's called the Audio Spectrogram Transformer. And this model takes a completely different approach. This one is really, I guess a more traditional speech processing model. But this one is different. This one will actually build a spectrogram from the audio clip. Okay, so it generates an image, and then it uses a vision transformer model, pretty much, to classify the image, and that delivers almost 1% extra accuracy over the Wave 2 Vec 2 conformer, which was state of the art. And so here in this space we can actually compare. So let's just grab one of those clips. So these are clips I recorded myself, and we can predict them with one model or the other. And we can see, so this takes maybe, well, I guess it takes 4 or 5 seconds. 4 or 5 seconds with the new model. And it has very strong opinions, and it's, we see those probabilities are really close to 100%. And if I try the other model, which is the one I originally used, most of the time it's going to be quite slower, and it's going to be less sure about the clips. Yeah. So, and that makes sense because this audio spectrogram model is about 8 times smaller than the Wave 2 Vec 2 transformer model. So of course it's going to be faster. So I think it's really interesting to see, again, this really clever idea of combining different modalities and different models to build something that's both much faster and much more accurate than the previous architecture. So again, the multimodal stuff I think is very, very exciting. And if we're going to look at the code, it's as stupid as you think it is. Yeah. All right. Yeah. So that's it, right? So you don't need to be a wizard to do this, which is great because I'm not. But I can still build fun stuff, right? So there you go. And of course, the last bit I want to show you, although I'm sure you're all up to speed on this, is the generative models. So text to image, stable diffusion, dream booth, and all those models. And here, this is literally, I guess, my first attempt at stable diffusion a few months ago. And fair enough, stable diffusion models are crazy complex. And here it just takes a couple of lines to use them. And this is what the one I built. This is the image I built. And everybody says, oh yeah, but okay, you run this a million times and you took the best looking picture. And you'll have to trust me, it didn't happen that way. I really ran, I guess, less than 10, probably 5 to 10 images, and I took this one because I liked it. I think it has all the elements that my prompt includes, right? The desert, the car, the diner, and the kind of sundown. It could be sunrise if you want to argue with that, but I think it's pretty cool. And this one is Stable Diffusion V1.4, which is already old, so I'm sure I could do better if I tried the newer ones. And then, of course, we can do all the stupid stuff, image inpainting, again, replacing parts of the image using a text string. So in this case, replacing a sweater with a Hawaiian shirt, or I could draw a mask. And so, for example, you could do, I think there's an example on the hub where they combine a segmentation model to they go from text to segmentation mask, and then they apply the segmentation mask for image inpainting. And again, those things work well together because they all share the same architecture and building blocks. So far, I've only talked about inference and using the models, but obviously, if you have a more advanced use case, you'll want to train and deploy. So that's I guess the family picture of Hugging Face right now. So of course, on the right-hand side, datasets and models. In the middle, open source libraries to train and optimize the model. So transformers, accelerate for distributed training, diffusers, which we mentioned, evaluate, which lets you score models against any kind of data set and any kind of built-in metrics. Optimum, which is our hardware acceleration library supporting CPU and GPU and ASIC training and inference acceleration. So we do a lot of work with Intel, we work with Habana Labs, we work with GraphCore and a few more that will be announced to accelerate training and inference using code that's almost identical to the Transformers library. We also have an AutoML service called AutoTrain, which you can use. Then, of course, you can deploy your applications on Spaces. And if you need prediction APIs, of course, you can go and deploy anywhere you like, build your containers, et cetera. Or you can use our own services. We have a free service, CPU only, called the Inference API, and we have a paid service called Inference Endpoint, where you can deploy models on AWS and Azure, on managed infrastructure with auto scaling, monitoring, and different levels of security, from fully public endpoints to fully private endpoints that you can only access through your VPC. And if you want, I would say, managed machine learning options, we also let you train and deploy on Amazon SageMaker using our built-in containers, and you can deploy from the Azure Marketplace to endpoints in just a few clicks, right? So that's the family picture today. Of course, it's going to keep evolving as we build new stuff, but as you can see, it's reasonably complete. So a few more links to get you started. So if you're completely new to Hugging Face, cannot recommend enough that you start with the tasks and the course, and that will take you from Hugging Face noob to Hugging Face expert, gradually walking you through the open source libraries and the use cases, etc. We actually have a chapter on computer vision. So if you want to learn how to train and fine tune those models, you can go there. Of course, we have documentations on the datasets library, which is important if you want to learn how to work with image datasets, whether they're hosted on the hub or whether you want to build your own image dataset. Of course, transformers and diffusers are interesting. The same stuff lives on GitHub if you want to see code, training scripts, examples, notebooks, etc. We have all of that. If you have questions or feedback, you can go to the Hugging Face forum, discuss.huggingface.co. And if your organization would like to move to the next level and engage in commercial conversations with us for support, custom training, etc., we'd be happy to do that. And again, you can contact us on the support page here. And if you'd like to stay in touch, you can find me on Twitter, while Twitter is still there. Medium, YouTube, LinkedIn, etc. Happy to connect. Happy to answer questions, tomorrow, next week, or in 3 months. Any time is fine. Thank you very much, Jimmy, for inviting me. I hope this was useful. I hope you learned a few things. If we have questions, of course, I'd be very happy to answer them right now. And thanks to everybody who listened.
Yeah, awesome. Thank you, Julien. So it does look like we have 2 questions in the Q&A. If you want.
Okay. Let me take a look. Is Vit already used in production somewhere? Oh, that's interesting. Well, I can only talk about what I know. So yes, we do have customers who use either Vit or, I would say, a vision transformer in production. Obviously, the challenge here is I guess is twofold. The first challenge is, fine-tuning the model on your own data, but that's not really complicated. Training on image data sets is very simple with our libraries. The larger problem is inference latency, right? And I think that's where CNNs still have an edge, and pun not intended. If you have really low latency requirements, or if you're deploying models at the edge, then transformers are still, a little bit too big. Although, in that battle of the classifier space, you'll find models from Apple, I think, that are, just a few megabytes. They have small versions, so mobile compatible versions of the vision transformers. So that's good, right? So yeah, so there's a question from Tom saying we can target edge devices for Hugging Face. So sure, I mean, there's no reason why you couldn't do it. I think again, the hardware requirements for transformer models can still be overwhelming for edge devices. So I guess generally there's a lot of work going on there in shrinking those models. Like I said, that those mobile net models are much smaller. I think the smallest one that I found in the Apple org is like 2.3 megabytes, which is amazing. So shrinking the models, and that can happen through, of course, using smaller architectures or using all the usual techniques, quantization and pruning, etc. And actually, that's what the Optimum library does. And then you have all the optimization tools like, Intel OpenVINO and so on, which we actually support as well in the Optimum library. So a lot of the work we do with the hardware vendors and with the customers is really on that topic. So yeah, you can consider transformer models at the edge. You just need to find one that will fit your hardware budget. Sure. So Michael asks, when playing with application in spaces, are user uploaded images ultimately archived or deleted, or no, they're not stored. Nothing is stored. Okay, so unless you want your space to store there somewhere, there's no other code than the code you're reading here. So so there's no data storage, there's no data usage. I think our privacy policy is very clear. None of the data you send either on spaces or on inference widgets, etc., is stored. So yeah, it's safe here. So George asks, you mentioned 4x better efficiency for vid compared to ResNets. Is that training? So yeah, that's what the vid paper says. They report 4x 4x training speed up compared to ResNet 152, and that was training from scratch. Generally, there seems to be some consensus that transformers are interesting if you have a ton of data. So if you have a lot, like 10 million plus images, and you train from scratch, you'll get better results with transformers than CNNs. On the other hand, if you just, if you have, I don't know, let's say 100,000 images only to train initially, CNNs tend to do better. Take that with a grain of salt, but I've read that in multiple papers, so there's got to be some truth. But back to your question, I think, to me, the huge benefit of transformers is transfer learning, so fine tuning, and a lot of customers are doing that. And sometimes, using even the few shot training approach, using just a few images, they get really, really good results. So unless you have a super domain specific, super exotic domain, I would encourage you to start from one of those pre-trained model, evaluate them on your own data, and maybe fine-tune a little bit. And that also stands for NLP, by the way. I think a lot of people are rushing to do initial training, when it's not really needed. So if you can live with a pre-trained model and fine-tune it, you'll get to production much quicker. And Tom is asking, can you compare the size of transformers to equivalent CNNs? The vision transformer, I'm quoting from memory, the vision transformer is about 300 to 400 megabytes. So that's pretty large, but like I said, you'll find some downscaled versions going to tens of megabytes, and apparently even less than that. So that's I think that's small enough that you could fit it on a small device.
All right, and I think that's our last question. So Julien, thank you very much for the presentation.
Sure. Well, thanks again for having me. It was really a pleasure to talk to the Computer Vision Meetup. I hope you liked it. I hope this was useful. Thank you very much.